So let's get started. So that was comparison of two different sampling approach, and for very weird distribution, and you saw that the behaviors are quite different. So we're gonna play with them today. So let's get started. Last time we only talked about the general idea of the sampling. We talked about importance sampling, and we stopped at the Gibbs sampling. And those are those are ways to approximate the posterior distribution when the exact inference are not possible. We also discussed in the previous sessions variational approach. So today we are going to continue our discussion about sampling, and let's see how far we can get today. So the demo that I showed at the beginning of the class was showing two different sampling approach. One that basically does local move, and the other one that uses the gradient. I don't think today we have time to get to the sampling approach that uses the gradient called HMC, Hamiltonian Monte Carlo. But we're going to discuss it next time. But it's a good demo to see that the behaviors of the sampling approach are different. Anyway, you have seen this slide several times in the past. When we were talking about the classical approach in the context of graphical model, we talked about the exact inference approach. Now we are in this module. We are discussing sampling method. Last week we finished discussion about variational method. So today and Thursday, most of my focus is going to be Monte Carlo method and different variants of the Monte Carlo method. So if you remember from last time, we discussed rejection sampling. And the idea of the rejection sampling was that, well, let's say that you are given a distribution, but you know that distribution up to a normalizer. So this is why I'm showing that as a P tilde. So the idea of the rejection sampling is that you come up with another distribution that is easier to sample from, called, let's say, QX, and so you also come up with a constant that if you multiply it by that density is going to include or acts as an envelope of the distribution for which you don't know the sampling. And the idea was that you introduce some sort of like auxiliary variable called y, and because this scalar is less than 1, you just use it as an acceptance or rejection of that sample. We also discussed that, well, you can always make this k gigantic to make sure that this value is always less than 1, but the problem here is that if you make very gigantic k, if you decide to have very gigantic k, you end up with rejecting a lot of samples, so your algorithm becomes very inefficient. We also discussed that this is a good method for one dimension, but when you're scaling into multiple dimensions, that it's not going to work that well. We talked about the idea of the importance sampling. What was common between importance sampling and rejection sampling was that, you see this theme that continues throughout the sampling approach, that we always come up with a distribution that's easy to sample from. And we said that many of this inference approach boils down to computing some sort of integral. And what if, well, this integral with respect to p that I don't know how to sample from it, but there is another distribution that I know how to sample from it, let's say Gaussian. Is it possible that I can change this expectation or computing this integral to another integral that I sample from Q and somehow weight the samples based on quote-unquote importance, and compute that expectation I'm interested in approximately. So the idea was that there's a Q that I can easily sample from it. I can multiply and divide it by that samples and come up with some weights. These are the important weights. And now my expectation with respect to Q become expectation with respect to samples that's drawn from the K, but they are reweighted. And that was the idea of the importance sampling. So this was the vanilla version of the importance sampling, if you guys remember. And I told you that it's pretty powerful approach, but again, it has a problem. If you just use the vanilla version of that for high dimension, it's going to be a problem because the value is going to blow up. So if to avoid blowing up of the variance, we have to make the tail of the Q very fat or very wide. And that, again, results into variance that are like our estimation that has a gigantic variance. And that's not what we want. So another idea to move away and use the structure of the graphical model was this modification that we made to the importance sampling. That the idea was that, let's say I want to sample from a chain. So there's the graphical model structure into the distribution I want to sample from it. Why not, as I move along the direction of the chain, I update my weights. And that was more efficient, and that results into particle filtering that we discussed last time. And we said that it has a lot of resemblance. Basically, you can think of this updated weight as a message that goes from one direction of the chain. And basically, the message goes, and like as you go from one end of the chain to the other end, you just update the weights accordingly instead of just assigning one weight to this. At the end, you end up with the weight for the entire chain, but it's incrementally updated, and it ends up to some sort of like a recursion tool that we discussed last time. So the summary so far is that this idea that there are reoccurring, these are basically the themes of the sampling approach are that, so the general ideas are as follows. So we don't know how to sample from our posterior, the object that we want to sample from, but maybe we can come up with another distribution that is easier to sample from. It's called proposal distribution. We mostly represent it by QX. You saw it in rejection sampling, you saw it in importance sampling, in particle filters, that we always come up with this easy distribution. But then, at least in the vanilla version of the importance sampling and also rejection sampling, we kept this Q the same. It was always the same distribution, which was not changing based on the current status of your samples. Why not changing it? And particle filter was, our first effort to change distribution as we go along the direction of the chain. Another, I would say the reoccurring theme in importance in sampling approach was introduction of the auxiliary variable. You saw that in the context of rejection sampling, that we have one variable that either we accept or reject the samples. But we saw that if we don't know the optimal the optimal weight K in rejection sampling, we end up rejecting a lot of samples. So it's very wasteful. So why should we discard all of the samples? Is there any way that we can use this? Also, we mentioned that in the high dimension, it's difficult, at least to use the vanilla version of this algorithm. So today, the focus would be how can we become more efficient? How can we use the structure of the graphical model because after all, the graphical model is about defining distribution for high dimension. How can we adapt this algorithm for higher dimension? Again, so you saw very first example of that in the context of particle filtering. And at the very end, not today, on Thursday, we're going to use the structure of the grid, the smoothness of the PX that you saw the demo of at the beginning of the class. So the focus of today is going to be these two modules. How can we change this QX, the proposal distribution, as we go along? And the second one would be how can we use the structure of the graphical model to do the sampling approach. Any question? Okay. So hopefully you guys remember this example that we had maybe 3 weeks ago about this annoying flight. If you remember, we assume the scenario that there are 3 doors and there is one smelly cheese and this fly is randomly walking through these doors. And showed, so basically if the current state of the fly is xt, is represented by xt and is door j, the next door that he jumped to is represented by a matrix. You can think of it as a CPD. And I told you that if you think of it as a random walk, in the distribution in infinity, if you look at the distribution of the places that this fly is going to, so it has a stationary distribution because it jumps from one door to another door. Of course, it's more likely to be at the door there's a smelly cheese, but the door next to it is more likely. The door further away from it, door 3, is less likely. And computing this stationary distribution boils down to computing this eigenvalue decomposition. We said that the stationary distribution is right eigenvalue of this distribution, if you guys remember that. So the reason I'm showing you this is that this is a very simple example. It was only 3 states, 3 doors, and I can easily write as a matrix. But the reason I'm trying to remind you about that example, that many of the algorithms that we are going to see today is about this random walk and about this stationary distribution. The equivalent of our stationary distribution here, which from this point on is not going to be just a matrix, because it's going to be the entire distribution, is going to be the distribution that you are interested in. So we are going to come up with the random walks that the stationary distribution of which is the px, is the one that you actually want to draw a sample from. Is that clear? At least the big picture? Okay. So the first approach that I want to discuss is a Gibbs sampling. So Gibbs sampling is, I would say, is very easy to implement. It's probably one of the, if you want to go through the path of the the sampling approach for inference, probably one of the first approaches that you should think about, because it's very easy to implement. So the general idea of the importance sampling is that, let's say that you have n distribution. Remember that we are interested in extending this model for high dimensions. And so here I'm just showing 2 dimensions because it's good to show. The general idea is that what if we just update one variable at a time? So if I have n variable, I just keep the rest of them constant, update one of them, go to the next one, update the other one, and so on and so forth. So the random walk, if you look at how the random walks look like, using Gibbs sampling approach is going to look like a bunch of Manhattan walks. So if I'm at the state xt, and I want to fix x2 at the constant value, and I want to update x1. So it's basically, if I look at the joint distribution px, I look at the fixing x2, I can look at the px, the profile at that point, and I'm going to draw a sample from. So in every iteration of the importance sampling is as if you're drawing sample from one-dimensional distribution. So, and again, so I'm going to fix the x2 at the iteration t, update the x1, and draw it from this distribution, and continue. So let's say the next sample is going to end up here. So next, I'm going to fix the x1 and draw x2. So this is how it's going to look like, right? So that's the general idea. One variable at a time. Is the general idea clear? General idea is very simple. So if you look at the random walk of the Gibbs sampling, is going to be every time you're just going to update one of the variables. If you have n variables, like you do n updates, and you continue.
How do you choose the next update? So let's say we are in iteration 0, right? So we fix.
Choose one of them randomly.
And then we found that the value of x1 given x2. And then what? How do we?
So let's say that you are at x1.
Yeah, let's say I'm there.
So yeah, at x2 you fix the x2 and you want to update x1. You look at the profile of the px. So I'm fixing x2, right? So this x1 is going to have a distribution.
Correct.
you draw a sample from it.
From, okay, yes.
From only like fixing one variable and continue. See, now right now I'm fixing x1 and drawing sample from x2, fixing x2 running from x1.
Of the next x is going to be from the
previous one. Yeah. So if you want to take a look at how the sample is going to look like, this is how sampling from Gibbs distribution is going to look like. Okay, so underlying distribution is just a normal distribution, and you see that the random walks are just walking to the different location of this normal distribution. This is how the samples from Gibbs distribution is going to look like. So, so what are the recipes? If you want to implement Gibbs sampling, what do I need to know? So the main ingredient is that you want to have an approach that you can deploy it for Bayesian directed graphical model and undirected graphical model. So if I want to fix all of the variables and update only one of them, so basically I'm fixing everybody else and I'm only updating this guy, right? So if in the context of graphical model, all I depend on is my Markov blanket. If I know, I don't need to know all of the variables. I only need to know my Markov blankets. So the Markov blanket are an undirected graphical model with all of these random variables that isolate me from the rest of the variables. So those are all of the random variables that are immediately connected to this. For undirected graphical model, it's very simple. What was the Markov blanket for undirected graphical model? Exactly. So my parents and my children and co-parents of my children. So if I fix those, I don't really need to know the other one. So why is it interesting? Because so you may think that, all right, I fix other random variables, but I need to sample from this marginal. How can I compute this marginal? Should I integrate out? So this problem might be as hard as the original problem, computing this marginal. But if you think about the context of graphical model, I'm only dependent on my neighbors. So it's basically my neighbors in MRF, an undirected graphical model, and in the context of graphical model, in the context of Bayesian net, on my Markov blanket. If I can handle that, I'm fine. So what do I mean by handle that? I mean that conditioning on my Markov blanket, if I can compute the marginal easily, and I'm going to show you an example of that. What do I mean by easily? I should be fine. So when I say easily, one way of being easy is that, well, if I can compute that marginal in the closed form. For example, if I have a conjugate model, if I condition my Markov blanket that has a closed form solution, I can easily sample from it. If it is not marginal and it's only one-dimensional, dealing with one-dimensional distribution is not that hard. You have already seen some example of that. For example, in the rejection sampling. If it's only one-dimensional distribution, you can use approximate approach such as rejection sampling. So also, you can think about a block. So each of these variables that you see does not have to be exactly one-dimensional. It can be a block of dimension that all make sense together. So what is the general idea? So how can I do that? So remember, the joint distribution. I can write any joint distribution with the chain rule. That if I want to single out one random variable, I can write it as condition on the rest of the variables. And this is the marginal of the rest of the variables. This is true about any distribution, right? It's just a chain rule. Now, if I had a graphical model, what this will look like?
Throughout the other nodes except for the blanket.
Exactly. So conditioning on the rest means that I only need to know all of the elements that are in my Markov blanket. If I'm MRF, my immediate connection, if I'm BN, there is a network, or like children, parents, and co-parents of my children. So the first term, which I'm going to represent this as for shorthand, I'm going to represent as xi minus xj, is going to be only dependent on my the Markov blanket of the xi. So you can view, so basically it's going to be the parents and all of the other terms that xi looks like on it, right? So this is going to be, if I have, this is my xi, this is going to be parent of the xi, and if I write the factors of that xi shows up, these are the other factors that xi shows up in the joint distribution of this guy and the joint distribution of this guy, right? These are all of the rest of the term. This is the term dependent on the parents. These are all of the terms that depends on the co-children, which is basically Markov blanket. The other terms that has to be taken care of is this normalizer, right? So you can observe the rest of the term as just a normalizer. So if I want to write a proposal distribution, I can write it as follows, that in every iteration, let's say an iteration, I want to update ith random variables. I have to fix the rest of the variable based on my previous iteration. This is my previous iteration. And update the jth one. So here this term says that keep the rest of the rest constant. And update the ith one. Right? So, and update the ith one is computing this distribution. And this would be my proposal. So the general idea is that if you are at the iteration L, keep rest of the variables the same because you want to update the Lth one, right? So this is why you need to introduce this delta function. This is just a way that I can write it mathematically, but otherwise during the implementation, what you're doing is just like you're not updating the others. And compute these marginals, this conditional. That this conditional is basically depends on only Markov blanket. Is the proposal distribution clear? This is how the proposal is going to look like.
Can you explain the mathematics again?
Yes. Yeah. So the intuition is this. In every step of the Gibbs sampling, you keep all of the random variables the same, except one of them that you update, right? So how can I write it mathematically? I just have to write a distribution that doesn't allow other random variables to change, right? So I'm going to write it as a delta function. I'm just going to say that if the other guy change, the probability of those are 0, right? So this is why I'm going to introduce delta, right? So this part enforces to keep the rest of the variables the same, except the ith one. For the ith one, I have to compute this conditional. That's all. This is just the same things that I told you at the beginning, just written in a sort of like a boring way. But we are going to use this notation later on. Okay, so now the problem here is that this is easy. It's just a delta function. And how can I compute this? And to compute that, I need to know the Markov blanket, and I should be able to compute this normalizer easily. So, and the idea here is that, let's say, in general, when I want to implement it, I'm going to do something like this. Let's say I have n random variables. I'm going to choose one of these n random variables randomly. So let's say I have 100 random variables. I'm going to say that let's choose randomly with some distribution that here I'm represented as a qi. Choose one of them randomly. And then update that random value. So the general draw from the xi would be first choose one of these randomly, and then update that one. So the final proposal would look like a mixture. That mixture says that choose one of the random variables randomly and update it. So the final proposal distribution looks like this mixture distribution. Make sense? Now, remember what I said at the beginning, that so we have two ingredients that you have to compute. First is computing this conditional. And to compute this conditional, we need the Markov blanket, and we need a normalizer. As long as our Markov blanket is not gigantic, we can compute this, and we can either compute the z in a closed form way or somehow approximate with rejection sampling. So let me show you some examples. Okay. Now, the next question would be, all right, so let's say you did this. Every time you choose one of the variables randomly, and you update that coordinate and continue. First of all, this is the draw won't be IID, right? Because I'm dependent on my previous iteration. That's number one. Number two is that, well, let's say that we did this. Who said that it's gonna be a stationary distribution? The stationary distribution is exactly what we want. So who said that? Like, I can come up with anything else. I can come up with, choose one of them randomly and then draw something uniform from the space. So what I'm going to do next, I'm going to show you why this distribution at the stationary converges to what exactly you want to sample from. So what is the idea should be to prove that the draw from the Gibbs distribution using this scheme converges to the distribution that we want to use from. Remember the annoying fly. Remember the annoying fly? We have this form of m v infinity, right? So this was our stationary distribution, and this was like proposal, right? So what would be the m here? Equivalent of m in this setting. How do I go with the proof that if I follow this procedure, the stationary distribution would be with the px? So I have some proposal distribution that says that if you are at the iteration t plus 1, you are dependent on qt, right? Okay. So if I want to prove that px is my stationary distribution, I need to prove that if I manage to sample from px, if I plug in px into p and I draw the next one, the next sample is going to be from p. So I'm going to get stuck at the px. Is the setup clear? So if I draw a sample from px and use that as xt, and then draw a sample from xt plus 1, as t goes to infinity, these should go to px. So basically, it's like the same equation, right? I want to say that, so here we have matrix vector product. So you want to say that if I draw a sample from Q, I have to prove this.
So that shows that P is in the stationary distribution of the Gibbs update. But how do we show that the Gibbs update is Markovian?
What do you mean?
So this just shows that it's a fixed point.
Yes.
And that, yeah, it is in the fixed point. But we need to show that the Gibbs update converges to its fixed point, right? And that there's
Yeah.
only one fixed point.
Yeah. So here I'm just only because I'm gonna only prove that's a fixed point. I'm not gonna show that this x point is achievable. But that's a very fair point. That I think you have to prove two things: that it's achievable and it's a fixed point. So here I'm gonna show. Let's only focus on the simplest part of the problem. But that's an excellent point. But is the setup clear? So you see the resemblance between this and this one? So here I kind of replace the matrix vector product with the integral. It's pretty much the same thing. And I'm saying that if I go and sample from Px, the resulting distribution is gonna be Px. If I prove that, that means that the Px under this proposal is a fixed point iteration. Okay. So now remember what the proposal distribution looked like. You guys remember Px? So this was the term that says keep the rest of the term constant. And we are going to sample from the conditional, right? And this was the distribution that I'm going to sample from, to draw one of the variables randomly, right? So this was our proposal distribution. You guys remember that from the previous slide. All I have to show is to show that if I sample from Px and use it as a previous point, the resulting distribution is going to still be Px. So all I need to do is to prove that. That's a fixed point. So, well, I already uploaded the notes online, but let's follow this. So all I need to do is that if I just plug that in Px, I can of course write the Px as Px and the rest of the variables. So far nothing has changed. So this part nothing has changed. So I just rewrite of the notation. And this term says, except I, the rest of them won't be accepted unless they are unchanged. Which means that this delta function is going to act like arguments, right? Otherwise, it's going to kill the rest of the term. So the result of that would be Px minus I can only be x prime. So what it does is that, so it says that don't change the other one, keep them constant. So you can easily substitute that Px I minus I. And also, what you see is that because of this effect, the rest of the variables is going to be the same. Because it says you cannot change the other one. I'm going to associate zero probability. So what it boils down to, you're going to have a distribution that your Px is going to be the previous iteration, your current updates, and this is going to be your conditional. So now remember that you're integrating over all of the x. If the rest of them are constant, what's the point of integrating over the rest of them? So all it does is that the xi is going to, you don't need to integrate the rest of them because they're constant with respect to dx. So your dx is going to be dxi because that's the only one can change. And this is what? This is just a chain rule. This is just a chain rule. And you're going to get, because these guys get out, because there's no xi in it, so this goes out. And because the rest of them are constant, this is going to be Pxi. This is just a definition of integrating on one of the values. It's just the definition of the marginal. And all you get is Px. So it was very simple proof that shows that Px is the station force. Now we have to go, so that is an important point that this is a fixed point, but is it achievable? And I'm not going to talk about that. But this is just to prove that if you come up with this algorithm, if you go to PX and you draw a sample from it, you're going to get stuck. And that is the general idea of this kind of random walk approach, that it says that if it converges to PX, it's not going to leave PX. So what you're going to do practically is that you draw enough sample from it with the hope that you have achieved the stationary point. In theory, if from theoretical point of view, it's really hard to prove that you have actually achieved the stationary. But this is what we hope practically. And in fact, there are very little theorem that says that. It's hard to, I talk about the practical aspect, it's very hard to prove that it's actually achieved. You don't have a certificate to say that oh, that is the stationary point. You just know that if it goes to the stationary point, it stays at the stationary point. Okay. So that was to show that, you that, okay, so this weird sampling, this weird random walk that we came up with is not just any arbitrary things. We have to prove that it has a stationary distribution that goes to PX. Now let's do some case study. So during the class, we used LDA as a case study. We derived the variational update for LDA. So we are going to come up with the Gibbs update for latent reach allocation. Hopefully by now you guys remember the structure of the LDA because you have seen it several times. But just as a reminder, remember that we have a document. The document has words, and we have a mixture that was proportional to each document. So if theta m was representing the proportion of the topic for document m, and phi k was k topics from a dictionary. Hopefully, if you guys remember that. And beta and alpha was the parameter of the Dirichlet. So if you guys remember from the last time, the exact inference of the latent variables inside of the document is difficult. Now we have to resort to inexact approach or approximate approach. I showed you how we can derive the update for variational. So today I'm going to show you how the update is going to look like for the Gibbs sampling. So today we are going to sample basically. I'm going to, for the sake of examples, I'm going to assume that alpha and betas are just parameters, they're fixed. And the proposal is to how can I sample from theta n and Zn. And the way I'm going to do that is I argue that if you have a sample from the posterior that has only Zmn, that's a sample from the true posterior, and integrating out or quote unquote collapsing the proportion of the topics and the topic distribution, ZMs are enough to give you a lot of information. In fact, all of the information that you want. So the general idea goes as follows. I want to draw a sample from the posterior of the Z's, PZ condition on the data and the parameters that here I'm using alpha and beta. I'm going to integrate out the topic proportion and proportion of the topic proportion, which is theta m, and the topic distribution, which is theta. So the way it works is very simple. So for each document, draw pi z from the posterior. That of course is hard to compute, but I'll tell you how we can do that, and continue until this Gibbs sampling converges to a stationary distribution, and then you have the draw from the Zm that is coming from the true posterior distribution. So you may say that why only Zm's? Why only? So remember what the Zm was. The Zm was the labels of the topic assignment for each word. I argue that that's all of the information that you want, because if, for example, if I have the labeling of the word to the topics, if I want to compute the posterior of the topics, what should I do? Let's say I want to come up with the distribution of the topic K, and I have the labeling of the words. What should I do?
Sum all the labels and take the ratio.
Exactly. So let's say if I want to go with the topic 5, I go and find all of the words in the corpus that has topic 5, and average them, and that's my distribution. What if I want to get the topic proportion for document 10? Either one of the documents. Well, not document. No, yes. Yeah, exactly. So just go to that document, look at the Z's, and see how many of those topic 1, how many of those are topic 2, and how many of those topic 3. That's going to give you posterior probability of P theta n given the rest. So if you have these ZMs, that's all you need. So let's only focus on that. So the way that full conditional is going to look like is basically, assuming that I draw things from the ZKs, it's going to look like this, that I just have to have a sort of a counter, that this counter says that the number of the instances of, let's say, word X that are assigned to topic J, not including I. So if I want to update the label for the word I have to condition on the rest of them. So let's say that I want to update the label for the word I. So I'm going to condition on the rest of them. I'm going to only focus on the document within, because of the Markov blanket, I only need to focus on the topic of my word, the word in my document that I belong to. And it's going to look like two update rules that are all very similar. So this multiplication of two terms that are very similar. And the reason they are very similar is that, so if I want to update the label of the word I, so let's say that I want to compute what is the posterior probability of the word I belongs to the topic K, condition on the rest of the words and the data. So this is basically just a Bayes rule. I have the nominator, which is the joint distribution plus divided by a normalizer. And if I write that, because of the structure of the graphical model, it's going to look like two multiplications that are both coming from the same form of the distribution. Remember, in my graphical model, I have a theta m. This is z, let's say, I. So I just dropped the document dependent. And this is the word that I have observed. And it's the phi k. So if I want to update zm, this is my children. This is the co-parent of my children. So if I manage to integrate this guy out and this guy out, I'm done. I'm not dependent on anybody else. So, but because of the conjugacy, because I assume the Dirichlet distribution for this guy and Dirichlet distribution for this guy, the update rules for the ZM are closed form. And that's the beauty of the conjugacy. So if I want to do Gibbs sampling, I only need to, for the current status of the distribution of the words, I only need to update my current approximate distribution for the Dirichlet and sample form. And updates are closed form because of the conjugacy. And this is because of the conjugacy between categorical and Dirichlet. This is an example that if you have a conjugate model, drawing Gibbs sampling is just conjugate updates. So far, we saw an example that only one of the variables get updated. And we saw that it depends on two things. First, our Markov blanket is not a very weird thing that we don't know how it's going to look like. And also, we can compute this normalizer. We saw an example in the context of a conjugate model that computing this z, remember that we needed to have a form that looked like this. Oops. This was like that. So remember that we need to compute this guy. And if it was a conjugate model, it's easy to compute. And this was my Markov blanket. But is it extendable for other type of models? So what if I cannot compute Z? What if it's not a conjugate model? So what can I do in those cases? So this idea of the random walk that at the end converges to a stationary distribution can be extended to the model that are not necessarily conjugate. And that basically boils down to the general idea of the MCMC approach. Monte Carlo approach that looks like a random walk and at the end converges to Px that you want to draw a sample from it. And from this point on, I'm going to give you a few examples that are more general approach and does not necessarily meet the notion of the conjugacy. So the general idea, our general goal is that we want to draw from approximate distribution that at the convergence, it draws sample from the Px. So the general idea holds. So the general idea is that I draw enough samples from Px that in infinity, my draws looks like they're drawn from the Px. At the beginning, it's not trustworthy because it hasn't converged. We don't know when it converged, but I'm assuming that if I wait long enough, it converges to a true distribution. And all of these algorithms looks like a random walk. So the Gibbs sampling can be viewed as a simple random walk that every time you update one of the random values. But nobody says that I only have to update one of them. I can update all of them at the same time. So what is the general algorithm? So the general algorithm is, so in an example that I showed you at the beginning, shows basically different flavors of this approach. That some of these approach are more local. So for example, here you're seeing Metropolis Hastings algorithm, and these are showing the level set of the weird distribution. These are, as you see, that none of these are Gaussian. They can be multimodal, and they have all kinds of the weird shape of the sampling. And as you see, each of these circuits as a draw from this chain, and you see the behavior of this algorithm. You see the behavior of this algorithm are quite different. For example, if you look at the vanilla version of the Metropolis, you see that it's very local. Sometimes get stuck at one mode, and if this distribution is easy, such as this, is going to cover the entire mode. But our goal is to make sure that we have an algorithm that explores everywhere. So make sure that it doesn't get stuck. You see that this one goes to this mode, sometimes jumps into the other mode. And in order to make sure that all of the modes of the distribution are covered, we have to use the structure of the graphical model. So first, I'm going to introduce a vanilla version of that, which is basically Metropolis Hastings algorithm. And then in the following sessions, we're going to talk about Hamiltonian Monte Carlo HMC approach that use the structure of the PX. So what is the general idea? So the general idea of the Metropolis Hastings algorithm is actually very similar. So in fact, you can view Gibbs sampling as an instance of the MH, Metropolis Hastings algorithm, where the proposal distribution says that there is no rejection. Just update one of the random values. There is no rejection. Here, the idea is somehow sort of like a mixture of rejection sampling and somehow you can think of it as a Gibbs sampling. You are going to reject some of the samples. So remember that you want to come up with the algorithm which is very general and can be applied for the cases that things are not conjugate. I cannot come up with a good normalizer. So this should be very, very general. So the algorithm says something like this. It's still a random walk like a Gibbs distribution, but sometimes you may reject the proposal. So if I want to write a proposal, the proposal is going to look like this. Either stay where you are, which I'm going to write it as a delta function, that don't move, reject this proposal, the new proposal called like x prime. Or go with a proposal that is dependent on your current location. So either reject it or accept it. So what is the probability of the acceptance? Probability of the acceptance depends on the current location and a new proposal. So basically, you have a function that's dependent on the new proposed jump point and the current point, and the chance of that, of course, either I accept it or reject it, so it should be a function between 0 and 1. And of course, I have to make sure that it's a complete distribution, so I just add the normalizer. So you can think of this as stay where you are. If I propose a new point, either stay where you are or jump to the new point with the chance of fx, x prime fx. And this is basically, you can view this as a mixture distribution. Mixture distribution between delta function and a new point. So this is basically, for the mixture, this is like a 1 minus the rest of it. Is that clear? Okay. So this is basically the general idea of the metropolis. But then you may say that, well, you have a lot of things here that are the design choice. So for example, the design choice is that how can I come up with this function? This function that says, based on a new proposal and a current point you have to accept or reject. You have to design F. And you have to also design a new proposal. How can I jump to the new point? So I'm going to discuss these two functions in the following. So remember what we were after. We were after a random walk that the stationary distribution converges to Px. So we have to design F and Q's so that at the end, the stationary point of this random walk is Px. So if you remember the annoying fly, what should I prove here? I have to come up with the F that the stationary distribution is Px. What should I do? What did I do to prove that Gibbs sampling, the stationary distribution of the Gibbs sampling was Px? I have to come up with the F that, oh, okay, sorry. Let's jump ahead of one slide. So first of all, I have to prove that this is a proper density, right? If I want to prove that it's a proper density, all I need to do is that it's a proper density with respect to x prime. If I integrate with respect to x prime, it should come up to 1. It should result into 1. And that's actually very easy to do because, if I make a derivative with respect to x prime, this is just 1 and it's just a constant. And these two cancels out because I added this term because I wanted to make it a distribution. So it's a density by design. The second thing is that I have to come up with the F and Q tilde, which is my proposal, local jumps, so that the stationary distribution is Px. So I need to prove that for a given distribution, if I draw a sample from it and plug that in, it doesn't change. The same things that we prove for Gibbs distribution. Right? This is very, very similar to MV infinity, V infinity, except that this looks like a V infinity, and this looks like our M. All right, so I have to design F and Q's that satisfies those this stationary point. So if I make this integration, basically I just plug that in Px into that one. So I just like multiply. So all I need to do is to Px. I just plug that in. All I'm going to get, this is basically the first term, which is basically this Px, this term. And for the Px, if I compute an integral of the Px delta x prime x dx, this is going to be just Px. So I'm going to get basically Px inside of this integral. So if I manage to satisfy this equality, then if I design F and Q's so that this equality holds, then my Px is my stationary distribution. So now I have a design choice. As long as we can come up with whatever F that you want, whatever Q that you want. You just have to make sure that this equality holds. One idea for this F function is as follows. So remember, these two terms look very similar, right? Except that X and XQs are inverted. So I can design F so that it cancels these two terms out and looks like this term, right? So all I need to do is that I can put these two terms in a denominator and these two terms in a nominator. That's very simple. Then if I just plug that in, I'm going to get the right-hand side. So then it's going to look like a function that looks like a ratio. And of course, I have to make sure that doesn't go beyond 1 because it's supposed to be a chance. It's supposed to be a selector. Doesn't make sense to go beyond 1. So I'm just going to cap it at 1. So you can view this as the probability of accepting or rejecting a sample. So all it does intuitively is that, let's for a second assume that these two are the same. So for example, if I come up with a Q x prime that is symmetric, which means that if I switch the x and x prime, it's not going to change. If it is symmetric, these two terms are going to cancel out. So my rejection sampling is going to look like 1 ratio of the px. Okay, so what does this one tell me? If I choose a qx that is symmetric, what does intuitively this rejection sampling tell me? It says that if the new point, that is x prime, has the higher density at the previous point, definitely accept it. If it is less, accept it with a chance. It's basically, if you have a density that looks like this, and you are here, this is x, and this is x prime, you're going up, that's a good point to explore. Accept it. If you're going down, maybe there is another hill somewhere else down the road. So you're exploiting where you are. Definitely you have to explore. Definitely you have to exploit, and you sometimes have to exploit. Sorry, you have to exploit, and definitely you have to explore. So you have to explore other regions with a chance, because there might be other good points in some other areas in the space. But if the chance of accepting a point is high, you should definitely accept it. So if you are going through areas that are high density, your proposal will be accepted. You're going through the area which is at a low density, unless it's very low, it might be accepted with a chance. So one of them is exploration, the other one is exploitation. So, and this is basically the intuitive idea of this rejection rate, that you try to explore areas that has a high density, and you also try to accept the areas that has a low density with a chance. Another beautiful things about this is that, remember, I don't know how the px is. I know px up to a normalizer. Remember that px is my p tilde x divided by the z. But the beautiful things about this equation is that it depends on a ratio. Even if I don't have the normalizer, I don't care, because this is basically the same as unnormalized version, right? Because the normalizer goes away on both sides. So you don't need to have a px to the exact value. Up to normalized is acceptable. And that's another beautiful thing about this, is that because you only need to px up to a normalizer, you're fine. Another beautiful thing about that is that for it is also the same about Q. You don't need to know the Q to the exact values. So here's an example. Let's say that you come up with a Q that you don't even know how to evaluate it. You don't have a closed form formula for that. But you know that's symmetric. You know that these holds. Then this cancels out, even without knowing. So what are the examples that this can be useful? Let's say that you come up with a proposal that's basically deep learning, and you just make sure that Q is symmetric. Then you don't need to evaluate Q. Let's say that you only know how to generate sample from it, but you don't know how to evaluate it. Example of that is that you draw a sample from, let's say, normal distribution, you plug it into your deep learning method and it jumps to another point. I don't know what the Q distribution of the new points are. All I need to know is that it should be symmetric. If you enforce that symmetry, you can plug it in as your new proposal distribution. And that's what makes this algorithm very general, because it looks like a ratio. The normalizer cancels out, and it has very simple form to evaluate. So these the defining fx in Metropolis is basically another way of writing this is that I can multiply both sides by the denominator, right? I can say that if this is the case, this is the equivalent way of saying that, right? Oops. That's the equivalent of saying that, right? So what is interesting about this, like I just wrote that equation in equivalent form. I just like massaged it a little bit by this was a ratio. I just bring that inside and said that okay, the value is not going to be fx, it's going to be multiplied by this. It's the same thing. But what you see here is that there's a symmetry here. If I switch x and x prime, it's going to produce the same thing. Right? So if I switch x and x prime here, I'm going to get this. So what it says is that if I have this equation and I switch x and x prime, I should get the same thing. And that is what is called detail balance. The intuitive idea of the detail balance is that, so that means that for every pair of the new point, proposed point and the previous point, it's called the x prime and x. Arriving at x, then x prime is the same as arriving at x prime and given x. That's what it means. As long as you satisfy this rule, you're fine. Symmetry is so when I designed a Q, which was, when I told you, let's say that x is symmetric, I just gave you an easy way of saying the same thing. But even if Q is not symmetric, as long as you can make sure that your design F and your design Q follows the detail balance, you're good. And that's all you need for Metropolis Hastings algorithm. So what are the ways that you can design Qs? As I said, like one idea would be, what if I point, so let's say that I'm in point xt, and I want to propose a new point. I can put this a normal distribution center on x prime with a small variance and draw from that. That's very simple proposal, right? Just wherever you are, wiggle it, wiggle it a little bit, and that's your new point. So the good things about that is that, so I have a design choice of having epsilon, the variance. If I make a variance gigantic, so my perturbation is going to jump it's going to jump huge, right? So if my variance is gigantic, the new point can jump hugely, right? And the problem here is that if you are around the area which has a high density, the high variance can actually hurt you because it can jump you away from the point that you were. And it was a good point. It was a high density area. So if your variance, if your epsilon is gigantic, the chance of accepting that is low because you're not using any information. You're just like adding a noise. So that basically justifies to have the epsilon that is tiny. But the problem of a small epsilon is that you're going to accept this with a high chance because you can add a little bit noise to that, and it's fine that you're going to accept it. But you're not going to explore the neighborhood very well. And that is the challenge of designing a good proposal. So, of course, I can come up with something that, with the current point, add a noise to it, either add a small noise to it or add a big noise to it. Small noise, you're going to accept it with a high chance, but you're not going to explore the space. Big noise, you're going to explore the space, but most likely you're going to reject it. Is that clear? So basically, it depends on how skewed the underlying distribution is. If it's very skewed, you need to, if you are at this point, in order to explore all of the space, you end up having a lot of small samples to go all the way from this part of the distribution to this part of the distribution. If you make a big jump, there is no guarantee that you go from this point to this point. You may, if this is just symmetric and doesn't know anything about the distribution, you may end up here. And the chance of accepting here is tiny. So, but anyway, so we will talk about how we can come up with a better proposal distribution in the next class. But the general idea of the general way to implement it, the skeleton of the Metropolis algorithm is extremely simple. The ingredient is that you have to come up with a way to propose a new distribution called Q. And you have your distribution, you want to draw a sample from it. You only need to know it up to a normalizer. And every time you just plug the new candidate into your PX, which is unnormalized, and you drop it, you also substitute that in your proposal, compute this ratio. If it goes above 1, you accept it. If it goes below 1, you flip a coin and accept it with a chance, and you go on. That's that work. So, but there are some practical questions about this. Is that is it better to move around one dimension or many dimensions? I mean, an example of going around one dimension was the Gibbs distribution. The difference between, so basically the idea of the Gibbs distribution was that in a Gibbs distribution, you make one local move, but there is no rejection. You always accept. You always accept, so there is no wasteful in terms of rejection. But all of your moves are very local. So now, to give you an example that why that can be a problem, let's say that you have a Markov random MRF, which looks like this lattice. So, I mean, for the people in the vision, let's say that this can be millions of points. So if you use vanilla version of Gibbs sampling, you are going to end up updating one of them at a time. And it is very painful because the pixel is not going to change one pixel at a time. It's going to be a block of the pixel at a time. So the vanilla version of the Gibbs sampling takes forever to converge. So you have to come up with a better proposal distribution. And instead of updating one of the variables, it's better to update chunk of the variables at the same time. Another question that you may say that, okay, so I just did it. So it's better to, okay, so I just did that. So it's better to draw a sample from a block of the distribution than just one variable at a time. And the same machinery applies. So in the LDA example that I told you, I showed you the collapsed version of that. I integrated out phi and theta, but you can update all of the theta, which is k-dimensional, and all of the phis, which are d-dimensional at the same time. You don't have to go through each of the iterations at the same time, but the general idea applies. So what? Yes.
I was just going to ask, can you also update multiple nodes that are far from each other, and then just assume that they're not going to influence one another, rather than do blocks of nodes near one another?
That's a good question. So in practice, so let's say that in MRF example that I gave you, so let's stick with that. So the way that people actually implement it is this. So your proposal can come up with any way of proposal distribution based on how creative you are. And that's basically so much of the literature of the sampling approach is basically depends on creativity of the author, that how they come up with the proposal that makes sense. So let's one of the examples of updating that is that first you can connect these nodes randomly to each other. You can say that, okay, I'm going to pair these two up and pair these two up based on, let's say, their intensity or something, right? I'm going to pair this up with some randomness. So I'm going to get the chunk of the variables, the cluster of the variables. And then instead of updating one pixel at a time, I'm going to flip the direction of the entire cluster. So first I make some clustering based on similarity of the pixels to each other. Do clustering after that and flip the entire cluster. That makes you a gigantic jump in a space that, so this algorithm called Sweat-and-Bank approach, and it's basically way faster than Gibbs sampling. Under the hood is Gibbs sampling. When it's the one variable, it updates chunk of variables. So, all right. So another practical issue is that, well, we proved that the stationary point of this sampling are the px. But how can I make sure that it's converged? Right? I know that I have to wait long enough, but how can I monitor? What's my diagnosis do? I have to say, unfortunately, there are not a very like a solid theory that gives you a certificate that you have converged or not. So the people who you're using sampling approach, basically it's more like you're cooking. You just put your stuff in the pot and let it boil. And you have to wait long enough and hope that it converges. But it doesn't mean that we have no diagnosis. So there are some diagnoses. So here are some examples of the diagnosis. What you can do is that you can run multiple chains at the same time. And of course, they can run in parallel because they are independent from each other. And compare the behavior of the chain on the held out data. There are some part of the data that I'm not using during my training, and I compute the log likelihood of that. So one behavior is that if the model is actually learning something and it's not overfitting, for the held out data, the likelihood should go up. If you see both of the chains are going up and it's staying at the top, you can hope that it has actually converged. Another thing that you can do is that, so what people do in practice here is that they let the algorithm run for, let's say, thousands of iterations and get rid of, so let's say that I run it for 10,000 iterations. And I throw out the first 5,000 because the first 5,000, my algorithm is just exploring this space. They're not useful. So that's called burned in. So those are burned in, and I hope that after 5,000 or something, I'm sampling from PX. And remember, in both Gibbs sampling and MH, that the consecutive draws are not independent, because in Gibbs sampling, the rest of the variables are constant. Only one of them is changing. In Metropolis, my proposal depends on the previous. So what I do is that I do thinning. The thinning is that, okay, I throw out the first 5,000. I end up with another 5,000. I'm gonna do throw out every 10 variable, so I'm gonna thin it with 1/10. So accept the first one, accept the 10th one, accept the 20th one, and accept the 30th one, and so on. So because they are far away from each other, I can sort of assume that these are independent. So if the chain has converged, so I do expect that the distribution of this and this block doesn't change much after thinning and after burning. So we have a statistical tool to make sure that they are not far from each other. For example, you can perform a hypothesis testing between these two, where the null hypothesis is that they are coming from the same distribution. If you reject the null hypothesis, then yeah, we'll probably need to run it for longer. If you see, for example, in a log likelihood behavior like this, it means that it hasn't converged because it's going up, the held out data is going up and it's going down. It means that the model is still exploring this space. I have to say that there are other methods for performing the diagnosis of this data. For the people who are going to use this in their research, especially people with the comp-bio background, I strongly recommend this book by Andrew Gelman. They have more diagnoses in their book. It's a really great book. And people who are serious about Gibbs sampling should definitely consider looking into this book. Another trade-off that you have, practical trade-off that you have, is that you can run this chain for, or you can run 10 chains at the same time. And then from computational resources, you may say that, should I run this for 1,000 iteration, or should I run it for 10,000 iteration and have more chain? So there should be some sort of a balance between these two, because if you run your chain for limited number, it hasn't explored the space long enough. If you let it explore for too long, if you let it explore for too long, you may waste a lot of computational time, because maybe after 5,000 it has converged to something useful. And by just sampling from that more and more, you're just like waiting here to see the result. So one idea that people do is that, first of all, they run multiple chains at the same time, and they run it long enough, making sure that the result has converged to something reasonable. And then the good things about that is that you can look at the log likelihood between different chains and compare the results. So the last point that I want to point out is that we have more or less similar problem in variational approach, because the landscape in variational approach is not close to convex at all. It's like totally undeterministic. We don't know it's convex, we don't know concave. And what we do there is somewhat similar. We run multiple initialization, and we run them long enough and monitor the log likelihood to see if it's saturated or not. So in that sense, I'm not worried that much about the convergence of this kind of approach. So the take-home message is this. If you are a practitioner and you are, let's say, if you are comp-bio and you care about the variance of your estimator and your model is not big, you should definitely consider a sampling approach, because the sampling approach, you can compute, it's not overconfident about the result, and it can give you the result that, at least if you care about, let's say, variance of your certain protein in your model, the results actually much more trustworthy than variational approach. If your model is gigantic, this probably does not work because it takes a long time to converge. Nevertheless, it's a great tool because you can try your simpler version of your model with sampling approach and compare the behavior of that with your variation. All right, so next time we're going to talk about the slice sampling and how we can use the structure of the smoothness of the PX to explore the space in a smart way. Thank you.